Hello, hello. Hi, everyone. So today we're going to go ahead and wrap up Unit 2 material. A couple of things just to let you know. Um, this stuff is going to go by pretty quickly because even though it's five and change pages of material, it's still going to be um like it's three sections in the 5 pages, you know what I mean? So it's gonna be quick, but just keep that in mind, okay? Especially for those of you that watch this video fast forward, just keep in mind because it will feel like I'm jumping all over the place, okay? All right, so let's start with inverse trig ideas, okay? So this is just a technical recap. Um, we have sine of x function that represents the y value in a unit circle, the cosine of x function that represents the x value in a unit circle, and then tangent of x will be y over x, right, of the unit circle. Now, if we take the inverse function, we have to consider the domains. The domain of the sine inverse function gets limited to negative pi over 2, pi over 2. The domain of the cosine function gets limited to 0 to pi, and the domain of the tangent function gets limited to negative pi over 2 and pi over 2. So, when asked to do inverse inputs, we have some quick ideas about how to do that from the unit circle. First, on the unit circle, what's the first value represents that? We would typically think of pi over 3. Over here, we have 2 pi over 3. Correct so far with these ideas. They're both in those domains, so we know we're clear. Let's keep going with tangent. Tangent, we have 7 pi over 4. What's wrong with 7 pi over 4? It's not in that domain. So that means we should adjust this by its period, tangent's period, which is just pi, until it becomes in that domain. So eventually, you'll subtract pi, and you'll subtract pi again until you get to either 3 pi over 4, or you could even keep going further, and you could technically do negative pi over 4. So either one counts. But note that 3 pi over 4 is still not in that domain, so it wouldn't give you that value. But negative pi over 4 is in that domain. So even though all these count, when in reality for the domain, we care about negative pi over 4. How about here? Well, you may say 11 pi over 6. However, we know that's not in the domain either. So we have to subtract a period. However, in this case, subtracting a period from sine means minus 2 pi. So minusing 2 pi, you get negative pi over 6. And that is definitely going to be that is definitely going to be our solution since it's inside that unit circle. Or in that domain, excuse me. This one's not really much. Let me box all the answers while I'm here. This one's not really much to think about. It's pi over 4. And this one is pi over 3. So these are all just unit circle ideas, practicing those inputs. So please recall unit circle evaluations, okay? So we're not going to go too much into the how for these derivatives of inverse trig functions. We're just going to go ahead and teach you what they are, and then go ahead and give you the sort of practice for all these. Okay, now keep in mind, we're switching in notation a little bit. Um, This, I'm gonna be honest, I kind of copy and pasted this part from my colleague, but the point that they wanted to make was that you're gonna be given a lot of trick questions. And the trick questions is because it'll be this, but something instead of x will be there. It'll be some function. So we can call u of x some function of x. So it's gonna better help us prepare for this. So for example, here, this is u prime on the top and the square root of 1 minus u squared. For this one, it's going to be negative u prime on the top square root of 1 minus u squared again. Tangent is u prime on the top divided by 1 plus u squared. Cotangent, it's going to be negative u prime on the top. And then again, 1 plus u squared. Secant is a bit of a weird one, is u prime, the absolute value of u, times the square root of u squared minus 1. And then cosecant is negative u prime divided by the absolute value of u times the square root of u squared minus 1. Okie doke. Let's go ahead and use all of these functions where they apply. So, first, find the derivative of tangent inverse of x squared. Now, in this case, we see that we're definitely going to be using the chain rule. Even though this already accounts for the chain rule, let's still practice chain rule ideas. Don't forget that the chain rule, if we define it as j of x for j of x is equal to f of g of x, that's going to be f prime g of x times f prime, or g prime, excuse me, of x. So over here, in this case, that u is going to be x squared. So we have, for our tangent function, that, or here, let me do u prime on the side 2x. So we have for our tangent function, we have 2x over 1 plus u squared, which is just x squared squared, which can be simplified to 2x over 1 plus x4. If you want to just use the chain rule plainly, well then you would just use this where let me go ahead and actually just write it here. Where u is equal to x, because then we know, and u prime is just 1. And you get 1 over square root of 1 minus x squared. Negative 1 over square root of 1 minus x squared. 1 over 1 plus x squared. Negative 1 over 1 plus x squared. 1 over the absolute value of x, square root of x squared minus 1. Negative 1 over the absolute value of x, square root of x squared minus 1. Okay? All right. So if we want to just use the chain rule, then we would first take in that value, which tangent, right? So x squared. So we would just, but we plug it in, it would be 1 over 1 plus x squared squared, and then times the derivative of x squared, which is just 2x. So 1 over 1 plus x to the 4 times 2x is 2x over 1 plus x4. So it's the same thing. However, like I said earlier, I kind of like this a little bit, but I did want to make sure we can practice chain rule ideas. Okay, let's go example 8. Example 8 says cosine inverse of 3x minus 1. Well, that's going to go ahead and be, we do let u be 3x minus 1, then u prime would be 3. So that means we can plug it in to this formula, just plain Jane. Negative 3 over the square root of 1 minus parentheses 3x minus 1 close parentheses squared. And that would be your answer here. And I forgot to box these guys as well. Same answer, but just to pinpoint that that's the answer. Okay, next one. Now this one involves product rule ideas. So let's go ahead and just recap product rule. We have f of x, let's just note it as x squared, and then g of x, which is just sine inverse of x. Well, f prime is going to be 2x, and g prime of x, excuse me, is going to be 1 over square root of 1 minus x squared. So we stack them with each other. 2x sine inverse of x plus x squared times 1 over square root of 1 minus x squared. And that's going to be your answer. Okay. Um, so this is just pretty much it. The only thing I advise you to be wary about is all of these little derivative tricks. I'm gonna provide you guys a formula sheet for the exam. I haven't decided if I'm just gonna embed it. I think I'm probably gonna embed it in the test. So you'll have it there. Like I'll probably make it one of the questions. So you just scroll to the top and it'll be there like question one, I guess. Well, I won't call it question one. But either way, if you have all these derivative rules, that's great and all, but you still gotta remember how to use it. So please keep that in mind, okay? All right, implicit differentiation. Now, in some cases, right, when we take the derivative of a function, we refer to it as y prime or dy over dx. Now, this works most of the time for finding the tangent of any classic function. What about not classic function? First, let's look at this function. Recall that this is a circle. And let's say the task at the moment is to, on any point of the circle, find that tangent line. Well, we know that means a derivative, but we don't have this as a pre-derivative. We need to write this as an f of equals. So let's solve for y. Solving for y, you subtract the x squared, 25 minus x squared, and then you square root it, plus or minus the square root of 25 minus x squared. Now here we have the issue. That plus or minus. That plus or minus is kind of annoying and makes derivatives not as fun. Well, that's where implicit differentiation comes in. What we can do with the implicit differentiation idea is that we can take the derivative of a whole expression. Recalling that though, recall that y is a function of x. So let's go ahead and do this notation first, and then we'll do another example with the other notation. But let's go ahead and lay this out. So we're going to go ahead and take derivative of each of these guys. So we know that we're taking derivative of x squared with respect to x. We're taking the derivative of y squared with respect to x. And then it's going to equal to the derivative with respect to x of the constant 25. Well, here we know that's just going to be 2x. And here we have a chain rule that happens. We have 2y, and then we know that y is a function of x, so we have to multiply it by y's derivative, which is just d over dx of y. And then here we know derivative that is just going to be 0. So let's go ahead and write this a bit more formally. I'm just going to rewrite it right now. And then you can go ahead and solve for dy in this way. We have dy over dx is equal to negative 2x over 2y. Simplify this just a tidbit and get rid of the 2's, and you have negative x over y. And here if we're provided with any point on this circle, we can find that tangent slope. So we can find, if we stop the circle at any point, we can find its trajectory on where it's going. Let's practice the other notation first, or a second now. So this is using dx. I'm gonna be honest. I even slipped it up here. I don't know if you heard me, but I like this notation better. You just prime the whole thing. So piece by piece, you'll go x cubed prime plus y cubed prime plus 6xy prime. Okay. Well, going from left to right, we know that is going to be 3x squared. This is a combination of chain rule. So we have 3y squared y prime. And then we have first that the constant escapes. And then that's just going to be product rule. So 6 times x y prime plus x prime y. Which we know that, well, this part can't really be simplified, so it just becomes 6xy prime. And x prime is just 1. So 6y. And now we can go ahead and write something where we get y prime equals. So I'm going to put all the terms on one side. We got 3y squared y prime minus 6xy prime is equal to 6y minus 3x squared. Then from there, we factor out the y prime. 3y squared minus 6x is equal to 6y minus 3x squared. And then we go ahead and divide this factor out to get y prime is equal to 6y minus 3x squared over 3y squared minus 6x. And that would be your answer. Now, if I'm going to be transparent with you all, for the next step in these, you probably will see this more often than this notation. It's a personal preference of mine, but I wanted to be transparent and say I think I am outvoted. I think that the more mathematicians will use this guy over this guy. So I'll try my best to show both and both, but just keep that in mind. If you prefer one over the other, I believe, yeah, both of these do have the dx, that's fine. But if at one point you see me flip back into this, I'm just going to apologize ahead of time. Right. So let's go ahead and do this one next. The derivative gets split. Is equal to the derivative of the other side squared. This is going to be a combination of chain rule, and this is going to be just a classic. Actually, we can just already do it. It's 2x. Here, we know that for sine, it's going to be cosine of x plus y, and then times the derivative with respect to x of x plus y. That derivative gets distributed basically. Dx of x plus dx of y. And then that's just going to be the number 1. And that's going to be just dy over dx. And then we solve for this guy. So let's go ahead and divide both sides by cosine. 1 plus dy over dx is equal to 2x over cosine of x plus y, and then minus the 1. Okay. Right. Let's keep it trucking along. We got two more of these. So I'm going to distribute the dx dy. I mean the dx is dy, just the dx. Xy minus cosine of xy equals d dx of 1. Here, that gets distributed as well. D of dx of xy minus d dx of cosine of xy. Then that's just going to equal 0. Okay. For here, we got a product rule situation. Dx of x times y plus x times d dx of y. See here, I feels like the prime notation would have been better. Sorry. I'll stop talking about it. Then we have d. Oh, wait, it's not true. We have. I was gonna erase it. We can't though. Sine of xy times d dx of xy is equal to 0. Oh, 0. That just gets simplified to 1, so y plus x times dy dx plus sine of xy. And because we know what this is, because we just kind of did it, I'm going to use that shortcut. Y plus x dy dx is equal to 0. Now I'm going to go ahead and use the fact that technically this is just glorified factoring. So that's what I'm going to do. And I'm going to have it to where it's 1 plus sine of xy times y plus x dy dx is equal to 0. Hmm. And then, because we know that this is 0, if I divide this out, 0 divided by anything is still going to be 0. So I'm left with y plus x dy over dx is equal to 0. Subtract the y. And divide by x. And that, oh, I forgot a box here. And that's going to be your answer. Okie doke. Let's do the last one. So now we have this guy. Let's go ahead and do that. For this, I'm going to go ahead and do prime notation. So we have y times the square root of x plus 4 prime is equal to xy plus 8 prime. So then we're going to go ahead and do a product rule. We have y prime times the square root of x plus 4 plus y times, I'm going to do it in parentheses just because that prime is not automatic. Then over here I have xy prime plus 8 prime, which is 0. But I'll go ahead and do that in the next step. Let's evaluate these two guys on the side. Square root of x plus 4 prime. First, I'm going to rewrite it as x plus 4 to the power of 1/2 prime. So it's going to be 1 over 2, and then x plus 4 to the power negative 1 over 2. And then xy prime is equal to y plus xy prime. That I'm just copying and pasting from the previous question since we had it appear right here technically. Okay. All right. Let's go ahead and plug all this in. We got y prime times that square root of x plus y. Or x plus 4, excuse me, not y. 4. Plus y times 1/2 of x plus 4 to the power of negative 1 over 2 is equal to y plus xy prime. Okay, so like we did in the previous example, gather up all y primes to one side, so we can go ahead and solve for that. Let's go ahead and get y prime times that square root minus xy prime is equal to y minus y times 1/2 x plus 4 to the power of negative 1/2. Okay. Factor out the y prime from this. Square root of x plus 4 minus x. And then I'm going to go ahead and fix that notation. 1 over 2 square root of x plus 4. Then we're going to divide it by that factor and we'll get a final answer. And that's it. So this implicit differentiation trick is probably going to sneak into some of your other materials. It will definitely sneak into differential equations if you guys go that far into your mathematics. But what it is introduced as right now is if we have a random shape on a function that's described like here, then we need to go ahead and learn how to, for any point, find that tangent line slope to better understand how that equation behaves and moves. All right, the last ones. So we're going to learn derivatives of exponential and log functions. A logarithm answers the question, what exponent do I put on a to get x? So we know that the log, defined like this, can be written as an exponent problem. That being said, let's go over some things that I hope is a refresher for log functions. We're using a natural log for a lot of these rules. I guess let me add some quick context for the natural log just real quick. ln of x is the same as log base e of x. And that's to say that ln of e is equal to 1. Or I guess I'll write e ln of 1 is equal to 1. They cancel each other out. Okay. First, ln of a times b can be written as ln of a plus ln of b. ln of a divided by b becomes ln of a minus ln of b. Then you have ln of a to the power of n can be written as n times ln of a. And then for square root, don't worry, it still has the same thing, but we just have to remember that square roots are just powers with fancy hats. So we still get it as 1/2 ln of a. Now, let's go over the exponentials. If we have an exponential function defined classically as a constant times e to the x, then its derivative is c e to the x. So notice how it does not change. That's normal. That's on purpose. However, if we have a custom exponential function with a specific base a, then its derivative becomes the same thing but times ln of a. Even if at one point you're to confuse it with e as a, you would do times ln of e, which we talked about is equal to 1. So it would turn out to be the same thing. Then for log functions, we have if a function is equal to c times ln of x, then it just becomes c over x. So that inside just becomes 1 over that inside. Then if we have c times log base a of x, then it's c over x times the ln of a. And similarly, if you're to accidentally forget that these are the same, and you do e, you'll still get c over x times ln of e, which we said is 1. So, some added details. Chain rule extensions. If we have it to where it's taking the exponential of some expression of x, then it would be that same thing times that expression of x derivative. Similarly, if we do c times ln of that expression of x, then we would just drop it down the bottom, like how the inside gets dropped down the bottom, but then it gets multiplied by g prime, but that expression's derivative. And then just one more extension. I think that got chopped up, and I just see it now. For here, if I have, some custom exponential to the power of some expression of x, then it's the same thing as here, but with the added ln of a. Similarly, if I have some expression log base a of g of x, then its derivative is c times g prime of x over g of x, and then times 1 over ln of a. Okie doke. We're on the last page. So let's go ahead and just put all these derivatives into these problems. All right, let's go. We got the derivative of 5 to the power of x. So that's just going to be 5x times ln of 5. Okay. If you ever get lost, just remember, if it was e, what would you do? Okay. Let's keep it going here. We can sneak out the constant. We can just write all of this over, or 1 over all of this, and then do multiply by this guy's derivative. Which, let me do that in erasable pen first. So multiply by this guy's derivative, which we know is 6x. And then if you were to simplify it, just a little bit, you would get 18x over 3x squared plus 2. Over here, let's keep it going. You got the negative constant sticking out. You got e 3 to the x and the derivative inside, which is just 3. So actually, I'm going to sneak it in right here. Okay, here the constant sneaks out. You get 5. You can rewrite the exponential. And then you do derivative what's inside, which is just 2x. So this can be written as 10x e to the x squared plus 1. Joke. Here we have log 2 of x. So that means we get 1 over x ln of 2. And that's just kind of a copy and paste of the formula. There wasn't too much complicated there. Forgot to box it though. Okay. Over here, we get 2 times 3 to the power of 7x, and derivative of that power is 7. So it becomes 14 times 3 to the 7x. Oh, and I forgot, because it's exponential, you also have to take, it's not exponential, excuse me. You also have to take into account times ln of 3. So times ln of 3. Okay, ln sine of x. Ooh, okay, that's ugly, but doable. 1 over sine of x times the derivative of cosine of x, which is just, times the derivative of sine of x, which I already said it is cosine of x, which we know is technically just cotangent of x. Here, we'll let the constant sneak out. We have ln, so 1 over 2x to the power of 3, and times this guy's derivative, which is just 6x squared. And then from here, you have the first step of rewriting it, so 18x squared over 2x to the power of 3. And then we have negative 9 over x, because that will cancel out, and this will simplify. All right, let's do some big ones before we wrap up this unit. Yeah. Here we have this huge expression. Um, let's go ahead and first rewrite this as 1 over the whole expression, so x squared sine of x divided by 2x plus 1, and then times the derivative of that inside, so x squared times sine of x over 2x plus 1 derivative. Okay? Let's do a step here. We know that that fraction can just be written as 2x plus 1 over x squared sine of x. And then from here, we know that that is the quotient rule. So we're doing x squared sine of x prime times 2x plus 1 minus, here I'm still gonna write 2x plus 1 prime times x squared times sine of x, all over 2x plus 1 squared. Okay, I'm just double checking my math. Okay, I haven't missed anything yet. Right, let's go and do these derivatives. We have this product rule, so we have x squared prime sine of x plus x squared sine of x prime times 2x plus 1 And then minus, I'm just going to cut to chase for that one. That's just going to be 2x squared times sine of x. Okay. All over 2x plus 1 squared. Okay. 2x plus 1 over x squared sine of x is equal to 2x sine of x plus x squared cosine of x times, or close parentheses, times 2x plus 1 minus 2x squared sine of x, all over 2x plus 1 squared. Okay, from here, I know you could simplify terms because we would see that if we multiply those two, we'll have 4x squared. And then I think it's the only thing I see that's simplifiable. But I don't know if it's worth it. Yeah. So let's just go ahead and say that this is the final answer. Okay. All right. Nothing too crazy, but it does sort of alleviate some of the worries. Um, it's because I did differently. I first split up the log function, but it does simplify. Mm, debating. You know what? I'm taking too long. Let me go ahead and stop here. Yeah, that's fine. Okay. Example 10. All right. This one I kind of overstepped, but we can still do it. This one has the added technicality of being a chain within a chain rule, but this time I will definitely use log rules to make this better. So before I even perform the derivative, I'm going to rewrite it as 5 ln of x squared plus 1. I can't split this any further because you can only split up when they're multiplying or dividing, and they're not doing either. So this derivative becomes 5 times 1 over x squared plus 1 times derivative of this was just 2x. So that becomes 10x over x squared plus 1. All right, that was a quick lecture. I'm gonna be in front of I'm still traveling, due to due to the sudden illness of a family member. So, please bear patience with me. Today I was spending a lot of time grading that I didn't actually get to finish, so I apologize for that. But I'm gonna try to finish grading all your test ones by tomorrow. Tomorrow Thursday. This is like live, by the way. I'm recording this as of Wednesday. So I'm gonna try to finish grading it that Thursday. Just keep that in mind. Um, let me know if you guys have any questions. And I'll see you all in the next video. Bye bye.